Welcome. Today we're going to look at solving initial value problems using Euler's method and Runge-Kutta fourth order, RK4. So if you're interested in that, then stay tuned. Okay, so let's begin by looking at this initial value problem. So what we have here is dy on dx equals minus 2x minus y, where y of 0 is minus 1. So in other words, when x is 0, y is minus 1. So we know we can solve this easily analytically because it's a linear differential equation. And so we'll do that, but the purpose of this is to solve this equation numerically today. So what we do is we let f, which is a function of x and y, we'll let that be the right-hand side when we have dy on dx on the left and everything else on the right-hand side. So we'll let that be minus 2x minus y. Okay, so that we have dy on dx is f of x and y. All right, so using a forward difference approximation of that first derivative, dy on dx, remember it's in the forward difference approximation, we have 1 on h, f of x plus h minus f of x, okay? And so we are putting this equal to f of x and y plus h on 2, y double dash of x, and so on. Okay, and so next what we're going to do is multiply throughout by h so that we clear this left-hand side, and rearranging so that we add this to both sides. You know what we should do is just call this is y of x, and this we'll call y of x plus h. Okay, and so let's multiply throughout by h and then add y of x to both sides. And so we have y x plus h equals y of x plus h times f of x and y plus h squared on 2 y double dash of x, and so on. Now, assuming that h squared is much less than 1, and that's what this symbol says, much less than 1, what we have then is y of x plus h is approximately y of x plus h times f of x and y, okay, with an error, epsilon, approximately h squared on 2 y double dash of at c, absolute value where c is in the interval xn to xn plus 1. Okay, so this gives an estimate of how far this is off, the error in that approximation. So now what we should do is let xn plus 1 be equal to xn plus h, and let's let yn plus 1 be equal to y of x n plus h, which in our case is yn plus h times f of xn and yn. All right, so from this one, the step size h is the difference. So we just have xn plus 1 minus xn, and there we have it. So Euler's method is to implement this sequence on an initial value problem. So let's go ahead then and have a look at our next page. So the initial condition y of 0 is minus 1 can be expressed as x0, y0 is equal to the point 0, minus 1. So this is our starting point here. All right, so let's choose step size 0.1. So this is the difference between xn plus 1 and xn. So then in this case, we have x1 is x0 plus 0.1. We have y1 is equal to y0 plus h times f of x0 and y0, but in our case, this is, well, I'll just fill it in here. So the differential equation, the right-hand side has minus 2x minus y. So this is y0 plus h times minus 2x0 minus y0. And so given that x0 is 0 and y0 is minus 1, we can sub these in here, and we get y1 is minus 1 plus 0.1 times minus 2 times 0 minus brackets minus 1. And so simplifying this, inside the brackets here we have plus 1. So 0.1 minus 1 is minus 0.9, I think, right? Okay, and then up here, x1 is 0 plus 0.1, which is 0.1. Okay, so now let's write this as a point. So x1, y1 is the point 0.1 minus 0.9. Okay, so continuing in this way, we've got a sequence of points. And so what we want to do now is match these points to the analytic solution. But what I'm going to do here is open up Mathematica and run this so you can see how I can easily generate these points. So our sequence started with, and now I'm going to use the subscripts. So we began with 0 and -1. Okay, so I'll put this into memory there. And then our sequence of better approximations was x subscript n plus 1, comma y subscript n plus 1 equals x subscript n plus h. And then up here, I need to enter that into memory also. And then for the next piece of it, we have yn plus h times f of x subscript n, comma, y subscript n. Okay, now I've expressed that as a function in this line. So up here, I will want to define that function. So I'm going to do it in terms of a and b. I need underscore here and here, colon equals. All right, now what this function is it's minus 2a minus b as a function of a and b. All right, so there's the function. All right, now we've set up everything we need to, and so what you would do is run a for loop, but I find that it's pretty easy to just run table or to tabulate these because I don't have an enormous list that I worry about putting into memory. It's going to be a short list, so I have no problem putting this into memory. So I'll just write table, and then let's just run this as n goes from 0 to 8. Okay, and so I have all of the points there that I got here plus one more. So if I take this to 7, then I'll get exactly that list. All right, so keep that there for a bit and let's move on to the next page. Okay, so next, let's solve that equation analytically. So we had dy on dx equals minus 2x, but let's take that 2x over to the left-hand side. So we want to take the y over to the left-hand side. Yeah, so we can call this thing linear. Okay, and so that's equal to minus 2x. So the coefficient of y is 1, so our integrating factor is e to the integral of 1 with respect to x, which is e to the x. So we multiply throughout by e to the x, and the left-hand side packs up as the derivative of e to the x times y, and the right-hand side is minus 2x e to the x. Okay, and so integrating this, now since we just want to do this analytically, let's just get Mathematica to do that part. So I'll just say integrate minus 2x exp x with respect to x. And so what we get then is e to the x times y equals minus 2 e to the x times x minus 1, and then we have plus c. So Mathematica leaves out that part of it. All right, so now we want to divide both sides by e to the x, and so we get y equals minus 2x plus 2 plus c e to the minus x. Okay, but y of 0 is minus 1, so we have then minus 1 is equal to 2 plus c e to the 0. E to the 0 is 1, so this gives us c is minus 3. Okay, and so we have then y equals minus 2x plus 2 minus 3 e to the minus x. Okay, so that solves that. We've just done all the details of that analytic solution there. All right, so next, let's give a little plot and explain geometrically what's going on. So the analytic solution to this might look something like this. All right, and so what's happening is we have our initial point, x0, y0, and what we do is we take a tangent and we stop on that tangent line when we have stepped forward that step size h, which is 0.1. Okay, so that might be here, and we stop on that tangent line when we've stepped forward 0.1, generally h. All right, so this would be x1, y1. All right, now we repeat this process, but the assumption here is that this is where the curve is, so we follow a tangent line from this point. Notice there's a little bit of a gap here because there's some error in that approximation that we use. You know, if I pull up this previous page, so the error is approximately given by this. So this is not perfect. There's a little bit of error here from the analytic solution. So we take a tangent, or in this case, it's just parallel to a tangent. we move ahead a distance of h, and we come up here following the tangent line, and we stop, okay? And then we repeat this process again, and so on and so on. So what you can see here is that the errors build on themselves. So the errors add up cumulatively, is what this says down here. Okay, so before moving on, I'm just going to plot the function that we got analytically together with the data we got, just to show you an exact Mathematica plot of this situation. So what we have then is minus 2x plus 2 minus 3 e to the power of minus x. So we'll plot this as x goes from 0 to 0.8. Have a look at that. Okay, so something like that. Now up here, I'll put this into memory as A, this data that we got. And down here, I'll put this into memory as B. Put that in memory as A. I want to write list plot A, and I'll just call that G. And then down here, we'll show G together with B. Okay, and so you can see what's happening. There's a bit of a drift here in the sequence of points because we're following that tangent, and there's a bit of error in that approximation. Okay, look, while we're here, I suggest that we change the step size to 0.01, and then that means I've got to change this n, okay, because you see it only stops at 0.08 if I keep that at 7. So I want to go to something like, what is it, 70? No, not quite. It'll be 79, won't it? 79 of these would get us to 0.8. All right, so if we do this again, let's plot this and then come up here and plot. You can see what's happening. They're now coming much closer to the analytic solution, but yet there's still a drift due to the cumulative error. Okay, and so let's now change this to plot style. Can I do this black? Because I think it's going to become difficult to see the difference in these two as we reduce the step size. So let's reduce that step size even more. So 0.001, and then now I have to go to 799 of these. Okay, I'll suppress the output. Oh, I see. You know what? This should just go up here in with this. Put this just all in one cell. Okay, so there we go. And now you can not see much of a difference between what we got numerically versus what we got analytically, because that step size is still is so small. However, again, there's still a drift, and if you went on long enough, it would become apparent. So down here at the end, I can see some little blue specks, but on this end, I can't see as much. Okay, so now we're going to develop an improved method, but we still use a recursively defined sequence. So here the global error is the absolute value of h squared over 2 second derivative at some c, where c is between xn and xn plus 1. So the global error is, because these things add up, the global error is n, where n is the number of terms we produced with the sequence. So n times h squared on 2 y dash of the subscript j, where cj is between xn and xn plus 1. Okay, so n is equal to x, the last one, minus x, the first one, over h. Okay, so to improve on Euler's method, we proceed as follows. So rather than using yn plus 1 is yn plus h times f of xn comma yn, we can do a little bit better. Remember what we do in taking a forward difference approximation. So if we had a curve, and so if this were xn here, this is xn plus 1, a forward difference approximation of the slope of this curve from here and approximating the slope function with the secant, right? And so this is just rise over run. All right, so you're stepping forward from xn to xn plus 1. All right, so in the forward difference, y dash at xn, we have 1 on h, y subscript n plus 1 minus y subscript n. And incidentally, this is y of x subscript n plus 1 and y of x subscript n. We put this equal to f xn yn plus h on 2 y double dash xn plus h squared on 6 times the third derivative at xn, and so on. Okay, now using the backwards difference from here, so we're approximating y dash x n plus 1, the left-hand side will be the same, but since this is a backwards difference, all the subscripts here will be xn plus 1 on the right-hand side. So we'll have f xn plus 1, y n plus 1 plus. Now this time it's minus h on 2, y double dash x n plus 1 plus h squared on 6, third derivative at x n plus 1, and so on. Okay, and now adding the two of these, so on the left-hand side we can see we have the same thing, so adding two of those, adding those up, we have two of those, so that's 2 on h, y n plus 1 minus y n equals f x n y n plus f x n plus 1 y n plus 1. Now what's happening here, so these don't vanish because we've got different numbers inside the brackets, but we can factor out the h on 2, and then we have plus h squared on 6 brackets third derivative at xn plus third derivative at xn plus 1. Okay, and so what we want to do next is multiply throughout by h on 2 and rearrange this, taking the yn over to the right-hand side. So what we get then is yn plus 1 equals yn plus h on 2 brackets f xn yn plus f xn plus 1 yn plus 1 in those brackets, and then we have h squared on 4 times this, and then we have h cubed on 12 times this, and so on, because this goes on and on forever because these were taken from Taylor expansions. Okay, so now what we want to do is, and that's our next page here, now replace yn plus 1 in this position with what we got from Euler's method. Okay, and so what do we get then? We have yn plus 1 is yn plus h on 2 f xn yn plus f xn plus 1 comma yn plus h f xn yn. Okay, those brackets in there, and then I need one right bracket there. So we'll chop it off here, meaning that we're chopping off the rest of this stuff, and of course that is associated with the error in the approximation. So there's still some error in it, but this will be a better or closer match to an analytic solution than what we got with just using Euler's method. Okay, before we go on to talk about Runge-Kutta second order, let's consider what we've just developed. All right, so we have y subscript k plus 1 is yk plus h on 2 f x k yk plus f of x k plus 1, and then this is the Euler part of that. Okay, so what I want to do here for you is implement this with Mathematica. So we'll go back to this little piece of code. Now what I want to do is take this back to point 1 first, and so this would be 7. Okay, so this is what we got with a step size of 0.1 using Euler's method. So now I want to use the modified version of this. This part of it here that I'm highlighting is the part that is different here in the modified version. So we need to change this in plus 1, but that is to add h to x subscript n there. Okay, now the yn part should instead be yn plus h times f x n y n. All right, now let's run that and compare. So you can see even with the step size of 0.1, this is much, much, much closer. And it's because the error in the approximation from step to step is much smaller in this version than in Euler's method. Okay, so now we'll develop RK2 using Taylor series. So Taylor's method of order 2. And the reason to do this is so that you have a better understanding of how RK4 can be developed using a Taylor series of fourth order. So we won't use the method that we're going to develop now in practice, but it's the key to developing RK4. So first note that the Taylor polynomial of degree 1 is, let's call it T1 in xn plus h centered about xn. So it's given by y of xn plus h times y dash xn. Okay, and so in other words, yn plus 1, it's approximately yn plus hf xn yn. So Euler's method is Taylor's method of order 1. Okay, so now let's consider the Taylor polynomial of degree 2. So here I put the 1 subscript there to be of degree 1. Now let's do one of degree 2. Okay, so let's put t subscript 2 xn plus h. So we've got y of xn plus h times y dash of xn plus h squared on 2 y dash dash xn, right? So this is truncated after the degree 2 h. Okay, so if we could use yn plus 1 equals yn plus h f dash xn plus h squared on 2 y dash dash xn, the error in each step would be absolute value of h cubed on 6, because that's what comes next in the Taylor expansion. So since we don't know the sign of it, we just take the absolute value of that. And so I'll put a third derivative xn. And so this is big O h cubed. So that's the order, the error in each step of this. Y dash xn is f xn yn, but we need a formula for y double dash xn. Now we do this by differentiating y dash, which is f of x and y. Okay, so let's recall the chain rule for g of t when the x and the y are both functions of t. So we have dg on dt is the partial derivative of f with respect to x times dx on dt plus the partial derivative of f with respect to y times dy on dt. So now if x of t is just t, then this would be dt on dt, which is 1. So we would get dg on dt is partial derivative of f with respect to x plus partial derivative of f with respect to y times dy on dt. Now y dash is g, which is f x of t, y of t. And so differentiating gives y double dash is df on dx plus df on dy, dy on dx. And so what we're doing here is replacing t with x, okay, according to that. So y double dash xn is f subscript x, replacing this notation for the subscript notation, xn yn plus f subscript y for this at xn yn. Now dy on dx, remember, is f of x and y. So this will be f of xn yn. Okay, so now we can sub into yn plus 1 is yn plus h times f xn yn. So just the second order Taylor expansion, replacing this with all of this right here. Okay, so let's do that. Yn plus 1 equals yn plus h f xn yn plus h squared on 2 brackets fx xn yn plus f y xn yn multiplied by f xn yn. Okay, and then I end that big bracket there corresponding to this one. So what do we do with the partial derivatives fx and fy in here? Okay, so what we're going to do with those is consider a tangent plane approximation. Okay, so I'll scroll this so you can see hopefully both pages. So we set f of x and y plus h on 2 fx of x and y plus h on 2 fy of x and y times f of x and y. We set this equal to a, some function a of h, x, and y. So before I finish writing this, let's note a, b, and c are functions of h, x, and y. Okay, so a times f, x plus b, y plus c. All right, so we're looking for functions such that we can replace this with this. Okay, so remember the tangent plane approximation. So f x plus b, y plus c, approximately f of x and y plus b, f subscript x, xy, plus c, f subscript y, xy. Now multiplying throughout by a gives us a, f, x plus b, comma, y plus c, as we have up here. So now what we want to do is match coefficients. So match this with this because these two are the same. All right, and so we see then that the coefficient of f of x and y is 1. So a is 1. The coefficient of f subscript x here is ab. So that says that ab is h on 2. And so since a is 1, b is h on 2. And then ac, coefficient of f subscript y, is also h on 2. So since a is 1, c is h on 2 times f. And so now that we have a, b, and c, we can replace multiplying throughout by h. Okay, so we are looking at this line and multiplying that by h. So we have h, f, x, and y plus h squared on 2 fx, x and y plus h squared on 2 fy, x and y times f, x and y. So we multiply that. So we can replace that then with h, f, x plus h on 2, y plus h on 2 times f, x, and y in this expression. Yn plus 1 equals yn plus h, f, xn, yn plus h squared on 2 fx plus fy, f, x, and y. Okay, now this part of it here, this underlined part, will match this, right? So these match. So then what we can do is replace this with this expression up here times h. So that is 1 times h, which is h, f, x, n plus b, but here b, h on 2, yn plus c. Now c we determined was h on 2, f, xn, yn. Okay, and so that is what should be in the box on my next page. Okay, so this is what we got. Now we can separate some of the pieces of this if we set this out somewhat differently. All right, and so let's let k1 equal to h, f, xn, yn. Let's let k2 be equal to h, f, xn plus h on 2, yn plus 1/2 k1. Okay, so what we have there is this. Looks like this part of it. And then so what we get, yn plus 1 is yn plus k2 plus some error in that Taylor series of order h cubed. So this is of order 2, since the global error will be OH squared. Okay, so this is RK2. Okay, so I see a typo, so I've scrubbed out that n plus 1 and yn there. All right, so now we're going to Mathematica to run this. So I have entered these functions, k1, k2, and then here for yn plus 1, we now have yn plus k2 of h, xn, and yn. So let's run this, and we can see that these dots are pretty close to the analytic solution. So let's compare this with what we got above. These look almost identical. Okay, so RK4 is developed in a similar way. RK2 has global error n times OH cubed, and so this is OH squared. So n being the number of steps. All right, Euler's method has a global error of OH, and so because presumably h is much less than 1, this is better than this because this will be smaller. So our errors will be smaller there than in Euler's method. There's an RK3, but RK4 is the most commonly used ODE IVP solver. So in other words, initial value problem differential equation solver. And remember what you get a collection of points that hopefully closely matches the analytic solution. Okay, yn plus 1 is yn plus h on 6 k1 plus 2k2 plus 2k3 plus k4. So this is RK4. It looks very simple there. We have 4 functions to set out here. And so this is developed from the 4th order Taylor expansion, making this RK4, where K1 is f xn yn, K2 is f xn plus h on 2, comma, yn plus h on 2, k1. And so these two are the same as in RK2. K3 is f xn plus h on 2, yn plus h on 2, k2. And K4 is f xn plus h, yn plus h, k3. So again, the derivation is similar to that of RK2. So what we do is use a Taylor polynomial of degree 4 of y of x. And so this is T4 xn plus h about xn Okay, so here is our Taylor polynomial of degree 4. We then use the chain rule, multivariate Taylor series, tangent plane or quadratic approximation, and so on, match coefficients, and we should be able to get this. Okay, so next I'm going to run this in Mathematica for you, but if you are a Matlab user, I've just written down by hand how you might put this together using Matlab. So go ahead and screenshot if you want that, and I'll scroll this down also. And there you go. That's probably a good screenshot there for you. Okay, so I have written this up in Mathematica. So you can see the K3 and the K4 are blue, so I haven't run this yet. It's the same differential equation or initial value problem as we've solved using the other methods, but this one's RK4. So let's run this now. Okay, and so with the same step size, you can see that these dots look like they're right on top of the analytic solution. So this appears to be much better than what we got with the others here. I can see with RK2, they're slightly under the analytic solution there. But with RK4, even with this massive step size of 0.1, we have solutions that are right on, it looks like at least, they're not right on, but it looks like they're right on the analytic solution. Okay, so let's change this now to 0.01. And remember, I need to change the end point in the tabulation to 79. And you can see that's beautiful. It's a very nice numerical solution to this differential equation. Thanks for watching.